Hello, bonjour, zdravstvostie, mambo. Welcome to the fourth tutorial of Statistical Mechanics, Algorithms and Computations from the Physics Department of École Normale Supérieure. This week we will study random numbers and the sampling of discrete and continuous one-dimensional distributions. We need to understand these relatively simple problems in order to attack the more complex sampling problems that we are interested in for their physical applications. For 3 weeks already, we heavily relied on random numbers upsilon generated through upsilon equals random dot uniform between 0 and 1. This means that we called on the module random of Python and used the function uniform between 0 and 1 to generate random numbers between 0 and 1 uniformly distributed with a flat distribution. We left out many things. For example, how these random numbers are generated on the computer, the most deterministic of all devices, and whether we can trust them. To get an idea of what random numbers really are, let us consider a baby version of a random number generator. It is called a congruential linear random number generator. Starting from a seed, an initial integer value, it generates a deterministic but seemingly erratic sequence of integers that are folded back into a given interval through a modulo operation. It is this modulo operation that gives the name congruential to this and this whole class of generators. Then these integer numbers are divided by a large number to give the familiar objects, the random floats between 0 and 1. Of course, this program is deterministic, and if we run it several times, we will obtain exactly the same output. Now, we can set the initial seed equal, for example, to the system time. And then the output of our random number generator will be a different sequence at each time that we run it. This is also done in the random.uniform that you have in Python, unless you take special precautions. Let us briefly discuss the properties of our naive generator, naive_ran.py. But as it is always more fun to find answers by yourself than to have them told to you, I ask you to download the program from the Coursera website and then to answer the questions. You may have to run the program in order to find them. So, question 1. The program naive_ran.py generates a sequence of integers idem and of floats idem divided by float of m. What is the range of the integers idem? Well, the answer is clearly that the integers idem are contained in the interval including 0 and m minus 1. This is done by the modulo operation, modulo m. Now, question 2. We have understood that the numbers, the integers idem, are between 0 and m minus 1. Does the generator generate all the numbers between 0 and m minus 1? Or does it leave out a few of them? Are there holes? Well, as you may find out for yourself, for example, by sorting the output of the random number generator along the first column, you see that all the numbers between 0 and m-1 are represented. Question 3. We have seen that the sequence of random integers idem is bounded. So sure enough, after a certain time, we'll hit a number that we have seen before. What happens then? Run the program and see for yourself. Well, the answer is very simple. The output sequence is periodic. If you hit a number a certain time, you will generate the same sequence as you did the first time. It is this, plus the fact that there are no holes in the distribution, that makes that this distribution is perfectly flat. You can learn about the Python generator by reading the documentation or by running this little program. In our applications, we need to sample integers and reals, but also physical objects from general distributions pi of x. This is, of course, what the Markov chain method is all about. But the direct sampling of discrete and one-dimensional continuous systems is an important subject that Michael will next treat in this tutorial. Before continuing, please take a moment to download, run and modify the program naiverun.py if you haven't done so already, and also to familiarize yourself with basic usage of random numbers by running this program.
Throughout this course, we used the Metropolis algorithm many times. As Werner explained in the first lecture, the Metropolis acceptance rate is given by P of A to B equals the minimum of 1 and the ratio of the statistical weights pi B and pi A of the states B and A. But what did we actually do in order to decide whether or not a particular move is accepted or rejected? This can be determined by comparing the acceptance rate to a random number between 0 and 1. If the random number is smaller than the acceptance rate, the move is accepted, and otherwise it is rejected. Of course, we do not even need to make this comparison if the ratio of the statistical weights is larger than 1, because then, according to Metropolis, the acceptance rate will be 1 and the move is certainly accepted. We have already used the Metropolis algorithm to sample non-constant probabilities. For example, in last week's homework number 3, you sampled non-constant distributions of hard disks. But now, let us use the Metropolis algorithm to sample a simple one-dimensional function, in fact, a Gaussian normal distribution. How does this look in Python? We start at x equal to 0, then we propose a random move with a step size between minus delta and delta. The acceptance rate of this proposed move, according to Metropolis, is shown here, and we have really understood that the minimum does not need to appear in the code. As we see, the algorithm samples the Gaussian distribution nicely, but it is much better to choose another route. We implement a direct sampling algorithm. In fact, a direct sampling rejection algorithm. Once again, we are now talking about rejections in a direct sampling algorithm and not about rejections of the algorithmic transitions in a Markov chain algorithm. So how do we proceed? Well, we can put our Gaussian into a box between minus x cut and x cut. And if you want, we can do this even on the Monte Carlo beach, in a setup which is only slightly modified from what we used in lecture 1. Just like the children threw pebbles randomly into a circle in a square to estimate the number pi, we can now randomly throw pebbles into our rectangular box. Whenever a pebble falls below the Gaussian curve, we accept it, and otherwise we reject it. So what is the probability that a pebble that has fallen at a position x landed below the Gauss function? Well, clearly this probability is proportional to the function itself, as there's the same number of pebbles landing at each position x due to the constant box height for all x. Then the fraction of accepted pebbles is proportional to pi of x. In Python, our newest pebble game can be implemented as follows. We first select a random position within the rectangle. Then we check whether it is above or below the Gaussian curve. And only if it is below, we accept it. With this direct sampling rejection algorithm, we again sample the Gaussian distribution very nicely. But note that we had to introduce this inelegant cutoff at -x cut and x cut. Rejection sampling can be problematic. It is not due to the presence of rejections per se, but because the rejection rate can become really enormous, even prohibitive. To see this, let's look at a function that is not quite as friendly as the Gaussian distribution. The distribution 2 over the square root of x. Maybe it troubles you that this distribution diverges for x to 0, as then the square root of x goes to 0, and 1 over the square root of x becomes infinite. However, such distributions exist, and Vivian will later show you how to sample them without problems using a simple sample transformation. But for our rejection method, that worked so nicely in the simple Gaussian case, this presents a real headache. And this is because we simply don't know what box size to choose. Should we set ymax equal to 1, to 10, to 1,000, to 1,000,000? Our rejection rate would skyrocket, and whatever value we choose, some part of the curve would still be above our box. Let's give it a try. We implement the rejection method, just like we did in the Gaussian case, and set ymax equal to 100. Although the result does not look too bad, in order to get a feeling for the potential danger of cutting off a divergent probability distribution at a finite ymax, we compare it to a Markov chain algorithm. Note that we do not need to introduce any cutoff, as the Markov chain algorithm does not have any problems coping with the infinite probability density. The program records the highest values of y and lowest values of x that it obtains, while it randomly moves along the x-axis between 0 and 1. This is the output of our program. In a few seconds of runtime, it goes down to values in x as small as 10 to the -7 and up to values in y of a few thousand, way beyond our chosen cutoff of 100. So should we actually use this Markov chain algorithm? Alberto in a few moments and Vivian later will show you that this is not at all called for. So before continuing, please familiarize yourself thoroughly with the way the Metropolis acceptance probability is implemented. Furthermore, take a moment to download, run and modify the programs we just discussed. On the Coursera website, you will find markovgauss.py that implements the Metropolis choice directly, and also a graphics version, markovgauss-movie.py. Furthermore, you will find the program rejectDirectGaussCut.py. Note that it has the word cut in its name, as we have to cut off the tails of the distribution at -x cut and x cut. In this example, this was not a problem, as the distribution is suppressed exponentially for large absolute values of x. There's also the program reject direct inf square root cut.py. Now we had to introduce a cutoff in y, and it was not exponentially small. This is really dangerous, and we must avoid it at any price. Before Alberto will next introduce the method of Taylor sampling, I invite you to take a look at Markov inf square root movie.py and take it apart, just in case you still doubt the existence of divergent distributions. Get it to run for other values of the exponent. Positive ones, pi proportional to x, x squared, x cubed, for x between 0 and 1, but also for negative ones, pi proportional to x to the minus 1/2, x to the minus 1, and x to the minus 3/2, again for x between 0 and 1. There are many strange phenomena to observe, and we will get back to them in week 10, the final week of this course.
Sampling non-uniform finite distributions as an archetypal example in what we call the Saturday night problem. As discussed by Werner in lecture 4, we imagine to have k possible evening activities, and we do not feel equally enthusiastic about them. Go out with friends, visit family, do your homework, sports, laundry, and so on. We know all the pi k probabilities, but we can still have troubles in deciding what to do. This means that we have trouble in sampling the probability pi 0, pi 1, pi 2, and so on. We can adapt Mikhail rejection method, and instead of sampling x between minus x cat and x cat, we can draw random numbers, integer random numbers, 0, 1, 2, k minus 1, select an activity which will be accepted if the pebble fall inside the red box. This occurs with a probability which is proportional to the weight of the activity. As Mikhail explained, this algorithm can have problems because of the high rejection rate. But for the Saturday night problem, this is okay. We can program the algorithm and plan our activities week by week. Bad luck. Let's look again to the last figure. You can see that the number of pebbles you should draw before having a single hit is typically equal to the ratio between pi max and pi average, where pi max is the maximal weight and pi average is the mean value between all the activities. This number can be very large. The tower sampling method is much faster and much more elegant. Instead of placing the box one next to the other, we pile up them one on top of each other, and the pebble is drawn from the bottom to the top of the tower. Once again, you choose your activity with a probability which is proportional to the weight of the activity. But the algorithm is much faster and the output is statistically the same. In Python, this gives the following rejection-free program. How we can actually find the box J where the pebble falls? For a small number of activities k, we can just go through the ordered table pi 0, pi 1, pi 2, and so on, until we find a j for which pi j minus 1 is smaller than upsilon, which is smaller than pi j. For larger k, it is better to use the bisection method. We should first check if upsilon is smaller or larger than pi k over 2, and then cut the range of possible indices j in 2 for any subsequent iteration. After log 2 of k operation, we will find the box, and this number gives the complexity of the algorithm. The tower sampling method is quite amazing because it implements a rejection-free algorithm for sampling, but is not optimal. The best method to sample discrete distribution is the Walker's algorithm. Let's consider the colored box in the figure. They represent the discrete distribution that we want to sample. And let's arrange them in a special way. We first compute the box height average as shown in the figure. There are bigger boxes and smaller boxes than average. Take one bigger box and a smaller box. Put on the top of the smaller box the bigger box. Cut it off at the average. Return what is left on its original position. You can continue and repeat this operation for other bigger boxes and other smaller boxes, like here and here. At the end, you will have a boxing scheme where for each position you have at most two boxes which adds up to the average. And now sampling is very easy. You notice that the logarithmic complexity has improved. We achieved a sampling method that takes a constant work per pebble for an arbitrary number of evening activities. And this ingenious algorithm can be programmed in Python in a few lines. Sampling a discrete distribution is so easy that you can think that to sample a continuous one-dimensional distribution, you should cut it up in small boxes and use the tower sampling or the Walker algorithm. This is not so. In fact, next in this tutorial, Vivian will show directly the continuum limit of the tower sampling and come up with very nice and amazing algorithms. But before listening to him, please take a moment, download, run and modify the programs we discussed in this section. Here you find the tower sampling method with the logarithmic search that locate the boxes. Here we find also the ingenious algorithm by Walker that produces the nice two-slate parquet.
In the final part of this tutorial, let us now take the continuous limit of the discrete distribution. This corresponds to cases where, instead of having a finite or enumerable series of probabilities pi 0, pi 1, pi 2, and so on, you have a function, a distribution pi of x, which is a function of a continuous variable x taking values inside the real line. To sample such distributions, let's come back to Alberto's tower sampling trick and remain with a discretized version of the function for a little while as described here. To apply Alberto's methods, we take the different boxes with colors indicated here, red, green, blue, yellow, pink, and place them on top of each other. With respect to the Saturday's night problems, here each box corresponds to a position x rather than to a specific activity. to keep track of these x positions, the best way is the one which is displayed here. Again, if we place a pebble randomly between the bottom and the top of the tower, that we can take equal to 1, we will fall in the red box with a probability which is proportional to the height of this box. But this is exactly what we want. Using this scheme, one can trace from the position of the pebble to the box and to the position x that we want to sample according to the distribution which is discrete pi of x. This is what is displayed here. Now let's make the discretization finer and finer. As you observe, there is an envelope which develops around the tower construction, and the value of the envelope at a given position x is in fact simply the integral of the distribution pi of x up to this point. In fact, in this example, we have taken pi of x to be a Gaussian normal distribution. So, this means that we have a second algorithm that we call Gauss transform.pi to sample this distribution. It is a bit complicated because we first have to compute the integral of this function. Sometimes we can compute analytically the definite integral between minus infinity and x. For the Gaussian distribution, however, Werner's tricks does not work. It only works between minus infinity and plus infinity. Fortunately for us, the definite integral, which is called the error function and which is displayed here, has been studied by mathematicians for centuries. Although it cannot be reduced to a simple formula, we can evaluate it numerically with high efficiency. But now, wait a minute. We don't need this function. So, generically, let's call phi of x the integral of the distribution pi up to the position x. We don't need the value phi of x associated to a given value of x, but rather the contrary. We need the position x corresponding to phi, which is the random number between 0 and 1. All in all, we will need the inverse function of phi of x. Again, for the Gaussian distribution, the inverse error function cannot be reduced to a simple form, but it can be evaluated numerically as displayed in this program, where its value can be computed by a simple call to the rf_env function. The output of the program is shown here. To summarize in a mathematical way the discussion that we have had up to now on a specific example, let us make explicit the correspondence between the discrete and the continuous cases. As displayed here, the first step consists in computing the definite integral of pi between minus infinity and x. This is the function that we called phi of x. The second step, which is illustrated there, in the discrete cases, corresponds to determining the position at which the pebble has fallen into. In the continuous case, it consists in determining the value x, which corresponds to the random number upsilon distributed between 0 and 1. Now, let us remark that the procedure that we have described up to now is in fact the sample transformation described by Werner in this week's lecture, lecture 4. In any case, the two hurdles that we have at hand, computing the integral and solving the equation phi of x is equal to upsilon, can be overcome in general for one-dimensional distribution with various degrees of rigor. Sometimes the integral can be computed analytically, sometimes one has to resort to numerical integration and to interpolations. Let us also remark that if pi of x presents divergences or singularities, however, its integral phi of x up to point x is in fact a much more regular function. Indeed, since pi is positive and can be normalized, phi is growing from 0 to 1 in a monotonous manner. This means, in the end, that the process we have described to sample pi of x is in fact very stable in general. As a second example, we'll now turn our attention to the case of the distribution pi of x is equal to a constant times x to the power gamma, where x is a real number between 0 and 1, 0 being excluded. A few minutes ago, Michael has studied this distribution in the case where gamma is equal to -1/2. This was a distribution which blew up when x was going to 0. Besides, we have already considered this distribution for gamma is equal to 2 in the program direct spheres 3D.py. Let us now apply the sample transformation to sample this distribution. This is what we use in the following program. With the proper normalization, the function phi of x can be computed, and it is equal to x to the power gamma plus 1. The sampling of the distribution is thus given by the following relation, which is x to the power 1 plus gamma is equal to upsilon, which means that x is equal to upsilon to the power 1 over 1 plus gamma, where, as usual, upsilon is a random number between 0 and 1 with a flat distribution. So, in the end, it means that to sample pi, we simply have to take this random number and to take it to the power 1 over 1 plus gamma. Isn't this remarkably easy? It took us a bit of brain work to think about it, but in the end, the results justify our efforts. Now it is your turn to download, run and modify the programs we have presented in this section. Have a look at Gauss transform.py and make sure that you have understood how the sample transformation works. Further, try out gamma transform.py and compare directly the results that you obtain to the two other algorithms, the Markov chain algorithm and the direct sampling algorithm that Michael presented earlier.
In conclusion, we have discussed in this tutorial random numbers and probability distributions and how to reshape them using rejection methods or transformation methods. We found great rejection-free sampling problems for discrete and continuous one-dimensional distributions and solved the direct sampling problem in these cases. Markov chain methods could generally be avoided. The situation is much more complicated in high-dimensional situations. For example, the hard sphere simulations that we did last week or the quantum problems that we'll next turn our attention to. In the meantime, have fun with homework session 4.